Okay, so last class so let us consider this particular example. I have an inverter driving a NAND and driving another inverter. Okay, this is, let's say, 1x inverter, this is, let's say, 64x, some larger inverter. This has some arbitrary size, okay, or let's say it's a unit gate. This is a unit gate. Now let me pose this hypothetical question to you. Suppose I were allowed to replace this NAND gate by a NOR gate logically, without changing anything in the logic. I am just allowed to replace the NAND by a NOR, hypothetically assume that, right? Then I have the following circuit. Okay, this is 164. What the size of the NOR is, I will not tell you yet. Okay, now I want to ask you a question. Is a NOR gate better or a NAND gate better in terms of delay? Assuming logic functionality is unaltered in both cases. Purely from a delay perspective, is a NAND better or a NOR better? Which one is better? Why? Huh? Huh. Correct. But the problem there is, I mean, that seems like a first correct intuitive step to the answer. But the problem is, I cannot even answer this question meaningfully unless I normalize the input capacitance of both these gates. Why? Because the delay of this path is determined by delay of 3 gates, right? Determined by delay of this inverter by this guy, or let's say I am looking at delay only from here to here. The last one is just a load, let's assume. Then it is determined by delay of 2 gates. One is delay of the inverter and then the delay of my device under the test, which is either NOR or NAND. Correct? Now delay of the inverter depends on what load capacitance that inverter is seeing. We just derived the whole expression, we derived. There is a load component to the delay and there is a parasitic component to the delay. Now in order to compare these two, I have to first say that this input capacitance offered by this NAND gate, so let me call it as C in, and this input capacitance should be the same. Only then the delay of this inverter and this inverter will be the same. Are you following me here? What I am basically saying is he made a point that the NOR gate had larger delay, but I can upsize by NOR gate. You understand? To now charge the same load capacitance, I can make my NOR gate bigger and then reduce my delay, because you saw that the load component falls off as 1 over k, right, of the delay. So how much can I upsize my NOR gate? That is the question I am trying to answer here. So the first thing I have to do is in order to compare a NAND and a NOR, which seems an otherwise meaningless thing to do, I have to first normalize the input gate capacitance of both these gates. Only then the delay of I1 in both cases will be the same. Delay of I1 should be same, because path delay is delay of I1 plus delay of my DUT, which could be delay of NAND or delay of NOR, right? So if I now want my NOR gate, okay, to have the same input capacitance as that of a NAND gate, okay, so I want to find out the following. So if I have a NAND 2 gate which has a size of unit size, what's the input capacitance here? 4C. Now I have a NOR gate. I am going to upsize this by a factor of alpha. What's the input capacitance of this NOR gate? Yeah? 5 alpha into C, because a NOR gate has transistor sizes 1144. So each input sees a capacitance of 5C, and if I upsize by a factor alpha, I will get 5 alpha C. Right? Now what is my aim? I want to make the input capacitance of these two gates the same. So I have to choose the alpha so that these two are the same. So therefore 5 alpha C should be equal to 4C. Therefore alpha should be 4 by 5. Okay. So here if I make this 4 by 5 times size of a unit inverter, I mean unit NOR 2 gate, then the input capacitance will be the same as that of a NAND 2 gate. Now I can ask the question, which path delay is lesser? Right? I can now ask that question because I have made sure that the delay of the previous inverter is the same now. It is seeing the same load capacitance in both cases. Right? Now tell me, what is the delay due to this NOR gate and what is the delay due to the NAND gate? So you can draw the equivalent thing. It's going to be R, right? This capacitance will be R and there will be a CL, right? Plus some parasitic delay. Okay, assume that the load capacitance is much larger than the parasitic delay in this case. We will not worry about the parasitic, it's a constant number. Okay, assume that CL is much larger than the parasitic capacitances. So the delay because of the NAND gate is R into CL. Right? This is my delay of the DUT. Similarly here, delay of my DUT for the NOR gate is what? It's not 5 by 4, it is resistance is, yeah, you're right, it will be 5 by 4 R because the size is, let's write that down explicitly, R by alpha, right? And alpha is 4 by 5 and therefore you will get 5 by 4 times R, and this has to drive my load capacitance, right? That 64x inverter, whatever it is. So this will be 5 by 4 R into CL. Now you compare these two expressions. Compare these two expressions. Obviously the NOR gate has 20% higher delay, right? Or 25%, correct? 25% higher delay compared to the NAND circuit. What is this telling us? It's basically telling us that if I have to present the same gate capacitance to my previous driver stage, then the NOR gate, whatever you do, will have a lesser drive strength on the resistance compared to a NAND gate. And this is not a function of upsizing the gate, nothing. It's purely because of the logic function that is being implemented. One is a NAND which has two NMOS stacks, other is a NOR which has two PMOS stacks, and therefore the gate capacitance is going to be higher for a NOR gate for the same drive strength. This is one way to look at it. Or the other way to look at it, like I told you, is if I want to present the same gate capacitance to the previous stage, then the NOR will necessarily have lesser drive strength in the resistance. That is what the meaning of logical effort is. Purely because of what logic you are trying to implement, you pay a penalty in terms of how much capacitance you will offer in order to obtain a certain resistance at the output. I cannot do both. What I mean is, if you take a NOR and say, okay, I will upsize the NOR and then reduce my delay to charge CL, right? I could. The other option, right? For example, here, I will say, okay, let me not do it this way. I will keep my unit NOR gate as it is, right? In which case, the delay to charge CL will just be R and CL, right? If I used a unit NOR, alpha equal to 1. But if you did that, then the capacitance that it offers to the previous gate will be 5C, whereas the NAND offered only 4C. So there is a trade-off in how much capacitance you can offer to the previous gate to how much drive strength I can get to charge a given load capacitance. This trade-off is captured by what is known as the logical effort. The inverter, because it has no stack, no NMOS, no PMOS stack, has the best logical effort of 1, defined to be 1. Okay? Any other gate, the moment you implement any logic, there is bound to be some sort of a logic stack, which means your capacitance goes up because you have already upsized the gate a little bit, right? By a factor of 2 or 3 or whatever it is, in order to normalize the resistance. That is what logical effort is all about. So if I give you two gates and say logical effort of gate A is less than logical effort of gate B, then it means that it is better to use gate A than gate B, because I can get the same drive strength by presenting a lower gate capacitance to the previous guy using gate A than gate B. Okay? Any questions? Yes. Yeah. Okay. No, I understand. So don't go into that. Okay, in that case, what I will do is I will not compare it with a unit NAND and a unit NOR. I will say you upsize the NAND also by 20x, and then this you compare accordingly. Then no problem. So don't worry about that aspect right now. Right? So let's assume that those bits are allowed. I'm just trying to give you an intuitive picture of what logical effort is. All I'm trying to say is you cannot achieve higher drive strength by upsizing the gate without resulting in higher input gate capacitance to the previous stage. Your delay will get affected either to itself, its own delay will get affected, or the previous guy's delay will get affected. This is the idea behind logical effort. So in fact, that's the reason why we have made it as why we express the delay as output load capacitance by input load capacitance. Fix that input load capacitance and then write it in terms of the topology of the gate. Right? So if you look at in out here, I can write down the delay in both paths. Let me do that actually, right? So we said delay was CL by C DUT into C unit by C inverter, right, plus some parasitic delay. In path 1, I had it like this. So delay of inverter I1 by the same formula out here is output load capacitance, right, that is C NAND, right, by this is a 1x inverter, C 1x thing into C unit inverter by inverter, that's the same capacitance basically, right, plus something. Similarly, the NAND delay will be, I have an inverter here which is 64x, right, C inverter 64x by C NAND into C unit by C inverter plus the parasitic delay. On the other hand, if when I took the second path, this is 1x, this was sized up by a factor of alpha and alpha was 4 by 5, but we ensured that these two capacitances are the same, right. So DI1 is C NOR by C1x, right, into something. D NOR is the, again the 64x capacitance, 64 divided by C NOR into C unit NOR by plus some parasitic delay. So what we ensured was C NAND and C NOR are the same. When we sized and we got this 4 by 5, 5 by 4 and all, we said these two are the same, therefore these two delays have to be the same. Now I can compare just the delay of the NAND and the NOR and tell you which of these two paths is better, is what we said, right. So this is the idea of logical effort. So what is logical effort formally? It's called G, the variable is G. It's basically ratio of gate cap of the gate, right, or the DUT, device under test, to gate cap of a static CMOS inverter with same drive strength. right? This term in the delay I am calling as G, logical effort. Okay? So, if I asked you, for example, what's the, maybe we don't have to do all that. What's the logical effort of a NAND 3 gate? NAND 3 gate, what is the input capacitance? Huh? 5, right? PMOS is, all of them are 2, each NMOS, because there are 3 NMOS on the stack, each NMOS will be 3. So net capacitance will be 5C. Okay? And I am now going to compare it with an inverter of the same drive strength. Remember, what is the inverter's capacitance? Yeah? Huh? Sorry? 3C. Therefore, logical effort is 5 by 3. Okay, if I have a NOR 3 now, what's the input capacitance? What are the sizes for NOR 3 first of all? NMOS is all 111, PMOS will all be 666. So net gate capacitance will be 7C. I am now going to compare this to an inverter with same drive strength, which is 3C. Therefore, logical effort is 7 by 3. So clearly, as you can see, more transistors you add to the stack, in order to get the same resistance, we already started upsizing those transistors. The net pull down resistance, we wanted to make it R. So therefore, we kept upsizing these transistors, which means that the capacitance offered to the previous stage is going to go up now, and that is captured by the logical effort. How much ever you upsize your gate by by increasing drive strength and all that, you will pay this penalty of drive strength versus capacitance that it is going to offer. So now let me ask you this question. Suppose I have a NAND 2 which has a drive strength of 20. That means what's the input gate capacitance? 20 into 80C, right? What's the logical effort of this NAND gate? Yeah? Same thing, because you have to underline this part of the definition. Compared to a static CMOS inverter with same drive strength. So if I want to compare this with an inverter with same drive strength, the inverter should also be stronger by the same factor, right? So therefore, I will make this stronger by 20x, and you will get a capacitance of how much? 60C, and therefore G will always be 4 by 3 for a NAND 2 gate with whatever drive strength. And that's understandable because it's called logical effort, which means it depends only on the logic that is being implemented by that particular gate. Clear? This may take some time. We'll do more examples in the next class. We'll start using it more and more, and hopefully it should become clearer as you go along. But go back and think about what I told you today, especially how I compared a NOR to a NAND. Why did I normalize the input capacitance? Why did I do only then you will see the whole picture emerging out of this. Okay, so we'll meet tomorrow. Tomorrow morning we'll start with the quiz again as usual. Okay, thank you.